9.1, systems of linear equations. So if we're going to deal with systems of linear equations, it might be a good idea to know what a linear equation is. So a linear equation is an equation that can be written in the form a sub 1 x sub 1 plus a sub 2 x sub 2 plus a sub 3 x sub 3 plus dot 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 a sub n x sub n is equal to b, where a1, a2, a3, a to, through a to the n and b are all real numbers. It is a first degree equation, noting that these variables x sub 1, x sub 2, x sub 3, x sub n, that those are all first degree. They're to the first power. They're never squared, cubed, or anything of the sort. So that is a linear equation in n variables, meaning you could have lots of different variables. Instead of writing x, y, z, etc., I just subscripted, so you have your constants a sub 1, a sub 2, a sub 3, those are constants. And your variables are x sub 1, x sub 2, x sub 3. We tend to deal with them a lot of times as just x, y, z, w, other variables, but there are times where we deal with them as subscripted variables, and that allows us to have an infinite number of variables if we so choose. So that's a linear equation. A system of equations is just a set of equations that hopefully relate to one another and can be solved, meaning you find a solution that satisfies all of the equations in that system. And then if you have a linear system or a system of linear equations, that means all of the equations in your system are linear equations. So they all fit into this form. Now we're going to start out by dealing with systems of two equations with two variables. So figure it as x and y. And if you have two linear equations, in two variables, meaning that there are two variables, so there are the same number of variables as there are equations, so you have a system of two linear equations, then there are three things that can happen. One, there is one solution, and that solution, we call that a conditional system, that given this set of things, that this one solution will work. So if you plug in the right value for x and y, say, then we will satisfy the equations. If we don't plug in the right value, then it will not satisfy the equation. So in that sense, they are conditional. The system is satisfied if you put the right solutions in, but otherwise it is not. And there's only one solution. So that's the first thing. And that you can think of as, since they're linear equations, they're just lines, right? So if we have two lines that intersect, that point where they intersect is the solution. That is the one point that is on both of those lines. The second possibility is that you have no solutions. And this we sometimes refer to as an inconsistent system or a contradiction. Meaning that there is no solution that will satisfy both of them. This happens when you have two lines that are parallel to one another. If they're parallel to one another, they are equidistant from each other forever in both directions, therefore they will never cross and there is no solution. So we call that an inconsistent system or a contradiction because there's no value that will satisfy both of those. Either it'll satisfy one equation, it'll satisfy the other equation, or it'll satisfy neither of the equations, but you won't find any solution that satisfies both of them. The third one is that you have an infinite number of solutions. And by an infinite number of solutions, what I mean is you have two lines that are the same. So your two equations represent the exact same line. In that case, every solution for the one equation will be a solution for the other equation. So there are an infinite number of solutions because a line is infinite. It does not mean that you can just choose any random ordered pair and have it be a solution, but there are an infinite number of solutions. There are also an infinite number of things that are not solutions, but an infinite number of solutions, and that's considered to be a consistent system. And I may be spelling inconsistent and consistent wrong. I think there may be an E instead of an A. You'll have to forgive me on that. Or an identity, meaning that they are the same. Remember when we were talking about the identity function, that was x equal to y. When the two were equal to each other, it was the identity. Here you're talking about a system of equations, and if the one equation is equal to the other equation, or is an equivalent equation, then you just get one line, and therefore you have the identity. And there are an infinite number of solutions. So we're going to go through and look at some examples for these, and we're going to look at a couple different ways that you can solve it. And we're going to talk about a third way that you can solve them, but I'm not going to do an example of it. So let's take a look at these and see what we can do. We got a little smearing from the eraser, but we'll survive. So our first method of solving a system of equations is substitution. Sub uses a B, not a B. There we go, substitution. With substitution, we solve one of the equations for one of the variables in terms of the other variable. Then we substitute that in to the other equation to get the other equation in terms of one variable. Therefore, we can solve for that variable and then plug it into the other equation and solve for the second variable and get our solution. So I know that's a lot of solving this variable for that variable to put it into this equation as this variable in place of that variable. Thus, we can have this variable which will help us to solve this other variable, and then we'll have both of the variables. So I understand that. So the best way to do this is actually look at a system of linear equations and use substitution. So I'm just going to grab my system of linear equations. So I have 4x minus 3y is equal to 14, and x minus 2y is equal to 1. So the idea is I have two equations and two unknowns. And I will state for the record that if you're going to be able to solve and actually get the solution, as opposed to a range of solutions, which we'll explain a little bit later, to a system of equations, you need to have as many equations as you have unknowns. So if we only have one equation, 4x minus 3y is equal to 14, we can't find x and y. We can either find x in terms of y, or we can find y in terms of x, but we can't use that to find a point on it without plugging something in and seeing what happens. So we can't solve for x and y. We can solve for x in terms of y, or we can solve for y in terms of x. If we have two equations, now we can solve for x and y and get a solution to it. So you have to solve a system of equations, you need to have as many equations as you have variables. So we have 2 equations and 2 variables, so we should be able to solve this. Now we're dealing with substitution, so what that means is I'm going to take one of these equations and solve such that I have a variable equal to an expression using the other variable. In this case, I see that x minus 2y equal to 1 looks relatively easy for me to solve for x. So all I have to do is add 2y to both sides, so I have 2y plus 1. So now I have the equivalent of x written in terms of y, 2y plus 1. So I used the second equation to solve for x, so I'm going to substitute 2y plus 1 into the first equation in place of x. So I'm going to go 4 times 2y plus 1, because x is equal to 2y plus 1, minus 3y is equal to 14. Now I have one equation with one variable. Multiply through, 8y plus 4 minus 3y is equal to 14. 8y minus 3y is 5y. Subtract 4 from both sides is equal to 10. Divide both sides by 5. Y is equal to 2. So now I have solved for y. Y is equal to 2. Now I can take this 2 and I can plug it into either one of the original equations to find x. And yes, it doesn't matter which original equation you plug it into at this point. When we got to this point, we solved this for x. In terms of y, we had to take this and plug it into here. Because we used this equation and reorganized it to get this, we had to plug it into the other equation so we could then solve for y. But now that we have a value for y, it doesn't matter which one of these equations we plug it into. We're just going to plug it in place of y, and that's going to allow us to solve for x. So I'm just going to use the top one. No real reason why. In fact, it would have been much easier to use the bottom one. But I said I'm going to use the top one, so I'm just going to plug it into the top one. So 4x minus 3 times 2, y is equal to 2, is equal to 14. 4x minus 6 is equal to 14. Add 6 to both sides. 4x is equal to 20. Divide both sides by 4, x is equal to 20 divided by 4 is 5. So we now have x equal to 5 and y equal to 2. So my solution is 5, 2. And although we have found our solution, we're not quite done with the work that we need to do. Because the other thing that we should do is we just solved it, but you should always go back and check and make sure this is really a solution. Remember, this must be a solution to both of these equations. If it doesn't work for either one of them, then it is not really a solution. If it works for both of them, then it is a solution. So let's plug it in and see. So 4 times 5 minus 3 times 2 is equal to 14. 4 times 5 is 20, minus 3 times 2 is 6, is equal to 14. 20 minus 6 is 14, so we have 14 is equal to 14. Check. It worked in that equation. So now let's do the other one. 5 minus 2 times 2 is equal to 1. 5 minus 4 is equal to 1. 1 is equal to 1. Check. So 5, 2 is a solution to both of these equations. and therefore it's a solution to this system of equations. And notice that we have a conditional system. There is one solution. 5, 2 solves this equation. So basically these two lines intersect at the point 5, 2. Now, another way we could solve this, and not one that we're going to necessarily deal with much, but I figured this actually isn't a bad one to work with here. We've got that 5, 2. So I'm going to keep that around for us. So we know that's the solution. So put it over here, 5, 2, just so we remember it's the solution. Another thing that we could do is we could graph these two equations. And this is solving graphically. We graph those two equations and we look for where they intersect. And where they intersect is the solution to this system of equations. Well, we can make that, we can either we can turn these into equations that we can work with easily to graph them, or we can just grab, well, if I grab some values I'm going to have to do anyway, so let's turn it into an easy way that we can do it. So let's put it into y equals mx plus b, because that gives me a slope, it gives me an intercept, and that makes it pretty easy for me to move around. So this first one, if I add 3y to both sides, I get 4x is equal to 3y plus 14. I subtract 14 from both sides. 4x minus 14 is equal to 3y. And then if I divide both sides by 3, I get y is equal to 4/3 x minus 14/3. So I have the first equation. My second one, if I'm solving for y, I'm just going to put a line there to separate that. So for y, I'm going to add 2y to both sides. X is equal to 2y plus 1. Subtract 1 from both sides. X minus 1 is equal to 2y. Divide both sides by 2. And I get y is equal to 1/2 x minus 1/2. So now I have an equation for the other line. So let's draw our grid here. Remember to number them. So I've got those numbered. So the first equation, the y-intercept is negative 14/3. That's negative 4 2/3. So negative 4 2/3 puts it about right here. And then the slope is 4/3. So every time you move over 3 in the x direction to the right, you're going to move up by 4. So I go 1, 2, 3. I'm going to go up by 4. So 1, 2, 3, 4. 1, 2, 3. I'm going to go up by 4. 1, 2, 3, 4. So now I have that first equation. The second equation crosses the y-axis at negative 1/2. So it crosses right here. And it has a slope of 1/2. So every time x goes over by 2, y goes up by 1. Up by 1. Over by 2, up by 1. Over by 2, up by 1. So I have this and trying to draw it as best I can. So I have my other equation. Now you can see already where a limitation comes with dealing with graphing. We know where it's supposed to intersect at 5, 2. I see here 5, 2 would be about right there. So my my drawing is a little off. Now I did make my own grids, and I'm not using a ruler or any straight edge, and I'm kind of guesstimating on there where it is. But we can see that graphing is another possible way to determine the solution, but it's not always a very accurate way. And the only time I really would consider it to be even a viable option is if you already have preset grids, so everything's nice and even, you have a straight edge to make sure your line is nice and even, and you're relatively sure that the solution is going to be made up strictly of integers, or worst case, 0.5, meaning that you're not going to be to the nearest tenth or to the nearest hundredth or anything of that sort, because forget trying to get that precise on a graph. So that is a second method we could use, not one that I suggest unless you are told specifically, solve the system by graphing. And if you do, please use graph paper and a ruler or straight edge just to try to get as accurate as possible. And assume, if you're told to solve a system by graphing, that they're going to intersect at integers for x and y. Because otherwise it's just impossible to get it. To come out with 3 2/7 from graphing, forget it. It's not going to happen. Okay, so that was finding the solution to a system of linear equations by substitution, and then I showed the graphing as kind of a side note. The other standard method of solving a system of linear equations is by elimination. So let me get rid of the substitution. Now, elimination is a more generic form of this. Some of you may be familiar with solving by addition. The idea being that if you have a system of equations, that if you can get the coefficients of a variable to either be the same or additive inverses of each other, then you can add or subtract those two equations and make that variable disappear. So elimination says, if your coefficients are the same, subtract the two equations and your variable will cancel out. If your coefficients are negatives of each other, -2 and +2, then if you add the two equations together, that variable will cancel out. That's elimination. Addition is sometimes presented for this because it simplifies the process by making so you always make sure that the coefficients are opposite one another, so you can add the two equations. Because as we know, when you start subtracting signed numbers, that's where people start making mistakes. So if you're subtracting two linear equations from each other, you're more likely to make a mistake than if you're just adding two linear equations to each other. So I don't care whether you go strictly by addition or whether you use elimination where you can either add the equations or subtract the equations. Myself, I use elimination because I don't care whether I'm going to add or subtract the equations, because I don't have problems doing either one, and I'm not more likely to make a mistake on a subtraction than I am on an addition. If I'm going to make a mistake, it's going to be some stupid mistake that I make that has nothing to do with the fact that it was addition or subtraction. Just me making a mistake. So, if I say elimination, you can think of addition. If you have somebody else say addition, you can think of elimination. It's basically the same process. So let's get a system of equations and see what we can do. So we have 2x plus 3y is equal to negative 1. And we have 3x minus 2y is equal to 18. Now, what I will state is when you're dealing with elimination or addition, you want to get your equations into standard form. ax plus by is equal to c. ax plus by is equal to c. So get it so that the variables are lined up in order on the left-hand side of the equation, and then on the right-hand side you have the constant term. Then we will start eliminating. Now in this particular case, I'm not already set up where I can eliminate one or the other. If I were to add these two equations, I'd end up with 5x plus y is equal to 17, and that wouldn't eliminate a variable. If I subtract them, I end up with negative x plus 5y is equal to negative 19. Again, I haven't gotten rid of a variable. So what I'm going to do is I'm going to force this to have the same or opposite sign coefficients to one of the variables. And I'm going to use x. So I've got 2x in the top equation, I've got 3x in the bottom equation. So I'm going to find the least common multiple of those two coefficients. If you have 2 and 3, the least common multiple is 6. So what I'm going to do is I'm going to multiply that first equation by 3. I'm going to multiply that second equation by 2. In doing so, I will cause these equations both to start with 6x. But I have to multiply all the way through, and this marker seems to be getting a little finicky, so I'm going to get rid of that. And so I'm going to multiply through this. So 3 times 2x is 6x. 3 times 3y is 9y. 3 times negative 1 is negative 3. So I multiplied through the first equation by 3. And I'm going to multiply by 2 through the second equation. 2 times 3x is 6x. 2 times negative 2y is negative 4y. And 2 times 18 is 36. So now I have equivalent equations. I multiplied both sides by 3. I multiplied both sides by 2. So they're equivalent equations, but notice that I have 6x and 6x. So if I subtract these two equations, so I tend to put like a negative sign off to the side, not in front of the 6x, but far enough off to the side that I recognize I'm going to subtract this equation from that equation. If it makes you feel better, put a little line there so you know you're doing an mathematical operation on that. This is very similar to what I do when I'm dealing with dividing polynomials. That I will put the negative sign off to the side far enough that it denotes I'm going to subtract this equation from that one, but not where it accidentally gets mistaken as a negation of this coefficient. So 6x minus 6x gives me 0x, so I've got nothing there. 9y minus negative 4y is the same as 9y plus 4y, which gives me 13y. Negative 3 minus 36, negative 39. So now I've got 13y is equal to negative 39. Divide both sides by 13. Y is equal to negative 3. So I just found y. Now, at this point, I have two options to find x. One, I can go back and make these coefficients match up. So I can then cancel them out and solve for x. Or two, I can go back and use substitution at this point, just plug this into one of those equations and find x. Because we're learning about elimination, I'm going to use the more complicated method. It would be much easier to just plug -3 into one of these and solve for x. But I'm going to use elimination again, so I'm going to cancel out my y's. Now you can see here that if you have 2x plus 3y and 3x minus 2y, that if I multiply the top equation by 2, and I multiply the bottom equation by 3, I'm going to end up with 6y up here and negative 6y down here. So I can cancel those out. So let's do that. So 2 times 2x gives me 4x. 2 times 3y gives me 6y. 2 times -1 is -2. And then in my second equation, 3 times 3x is 9x. 3 times -2y is -6y. And 3 times 18 is 54. Now we see that I've got 6y and -6y. So if I add those two equations, then my y's will cancel out. 4x plus 9x is 13x. 6y plus -6y is 0y, so that canceled out. And -2 plus 54 is 52. So I have 3x is equal to 13x is equal to 52. So if I divide both sides by 13, x is equal to 4. So now I have determined that the solution to the system is 4, -3 by using elimination twice. Well, that's good. We solved the system, but remember, the best thing to do once we've solved it is to test it out and make sure that it actually works. So we are going to plug this 4, -3 into each of the equations and make sure that it actually gives us what we want. So we have 2 times 4 plus 3 times -3 is equal to -1. 8 minus 9 is equal to -1. -1 is equal to -1. So far, so good. And then the other equation, 3 times 4 minus 2 times -3 is equal to 18. 3 times 4 is 12. -2 times -3 is positive 6. Plus 6 is equal to 18. 18 is equal to 18. And we are good. So we solved it by elimination, and then we checked to make sure it was a solution to both of those equations. So 4, -3 is the solution to this this system of linear equations. And again, we have that it is a conditional system because it is true when x is equal to 4 and y is equal to -3, but at no other point. Now, how do we determine whether we're going to use substitution or use elimination? And that is an excellent question. Because is there really a reason that we should use one other than the other? Should we learn them both? Or should we just decide which one we like better? And the answer is that you can, in general, use either method. Substitution and elimination, if you know how to use them properly, will work for any system of two linear equations with two variables. It'll work. So, is there a reason that I should learn both of them, or can I just choose the one that I like best? The reason that you would want to learn both of them, well, a couple reasons. One, I could require you to use a specific method to solve a system. And if you don't use that method, then you don't get full credit. So that's the penalty reason. The other reason is that sometimes a system of linear equations just jumps out at you saying, solve me by using this method, such as 3x minus 2y is equal to 7, and y is equal to 4x plus 1. If you are given this system of linear equations, common sense says, use substitution. You already have this equation solved for y. So just take 4x plus 1, substitute it in place of y here. Oh, sorry, that was supposed to be a 3x. Okay? I think I said it as 3x. So substitute that in for y and solve for x. Whereas if I did elimination, I would then have to put this into ax plus by equal to c form. Then I would have to see how I'd cancel, because in this case, that would mean I'd either have to double this equation, or I would have to triple this equation and quadruple that equation, right? So we run into all sorts of concerns with that. So obviously it's easier in this case, or you would think that would be easier in this case, to just solve it by substitution. Whereas, if you have something like this, 7x minus 9y is equal to 15, and 8x plus 9y is equal to 4, we should look at this and go, well, gee, I don't want to solve for one of these variables and have to plug in some nasty fraction. But look, I've got negative 9y here, I've got positive 9y here, so if I just add these two equations, y is going to disappear, and I'm going to be left with equation to determine one variable, and I can solve that. So we can see that there are times where one system, one method, either substitution or elimination, should jump out at you and say, this is going to be the easier way to do it. So should you learn both methods? Definitely. If for no other reason than the fact that it's going to save you all sorts of effort dependent on what system you're given. Because solving this by elimination, piece of cake. Solving it by substitution, dealing with ugly fractions and working that through, creating extra work for you. So let's try another one and see which we deem to be the easier method for that. So we have 7x plus 3y is equal to negative 5, and negative 14x minus 6y is equal to negative 10. Now personally, I look at this and I see a system that is not saying I want to use substitution. I see a system where I've got 7 and negative 14, 3 or negative 6. I'm seeing that if I multiply this top one by 2, I'm going to get some cancellation here. So it looks to me like an elimination problem. So I'm going to multiply that top one by 2. Turn it, so 2 times 7x is 14x. 2 times 3y is 6y. And 2 times negative 5 is negative 10. Okay, so I've got that start there. So now I see negative 14x and 14y. That's a good thing. So I'm going to add these two equations. Negative 14x plus 14x gives me 0x. Negative 6y plus 6y gives me 0y. Negative 10 plus negative 10 gives me negative 20. So I have 0 is equal to negative 20. Well, 0 is not equal to negative 20. So where did I make a mistake? The answer is I didn't make a mistake. This is an inconsistent system. Inconsistent system or a contradiction. We started to solve, and we came out with an equation stating that one thing was equal to something else. So we came out with a false statement. If you're solving and you don't make any mistakes, a system of equations, and you come out with a false statement, then you have an inconsistent system, which means that there are no solutions. You could come out with 0 equal to negative 20. You could come out with 4 equal to 5. If you come out with a constant equal to a different constant, then you have a contradiction, you have an inconsistent system, there are no solutions. So that's where we ran into this. The biggest mistake that people tend to make on this is they do negative 14x plus 14x, okay, 0x, they go, that cancels out. Negative 14y plus negative 6y plus 6y, they cancel that out, and then they say negative 10 and negative 10, oh, that cancels out, and they say it's equal to 0. And they come out with 0 equal to 0, and they go, what happened? But obviously what happened was you added, you subtracted. So be careful about those little mistakes. Let's try another one. Negative 9x plus 3y is equal to negative 24. And y is equal to 3x minus 8. So now I look at this and I say, well, gee, it already has us solved for y in one thing, so that looks like a substitution problem to me. So I'm going to plug this into the first equation in place of y. So negative 9x plus 3 times 3x minus 8, don't forget your parentheses there, is equal to negative 24. Negative 9x plus 3 times 3x is 9x. 3 times negative 8 is negative 24, is equal to negative 24. Negative 9x plus 9x gives us 0x, so we get negative 24 is equal to negative 24. And you say, no kidding. I already knew that, Mr. Davis. I knew negative 24 was equal to negative 24. But what we have and what just occurred is we came out with a true statement. We didn't find out that x was equal to some value or that y was equal to some value. We found out that some number was equal to itself. We may have gone through and solved and found that x was equal to x. So what does that mean? Well, that means we have a consistent system. Consistent, meaning that there are an infinite number of solutions. And that infinite number of solutions is the line that both of these represent, because these are the same line. Now, that told us it was consistent, it was told us there was an infinite number of solutions, but it's not sufficient to leave it like that. What I want to do now is I want to find a solution to this. And what I mean by that is I want x and y to be written in terms of one of the variables. And we already have that. We can say that x is equal to x, and we know y is equal to 3x minus 8. So the solution to this system of two linear equations is x, 3x minus 8. We can also solve the other way, and I could get it so that it's in terms of y, so I can add 8 to both sides, y plus 8 is equal to 3x, divide both sides by 3, and I get x is equal to y plus 8 over 3. So now I can say the solution to this is y plus 8 over 3 y. So that's the solution in terms of y. Give me an x value, plug that x value into 3x minus 8, and that's going to be a solution to it. So if x is equal to 2, 3x minus 8 is negative 2, so 2 negative 2 is a solution to these two equations. If I say x is equal to 5, 15 minus 8 is 7, so 5, 7 will be a solution to these two equations. If I say y is equal to 1, then x is going to be equal to 9/3 or 3, so 3, 1 is a solution to these two equations. So this is dealing with a system of linear equations where we have two variables and two unknowns.